volume and surface area of Doughnut, also called Torus. So basically in this video we'll try to use integrals to try to find the surface area and volume of this given shape over here. And yeah, it will be a lot of fun. We'll try to go with we will try to explain everything in really easy way and hope that will help you guys. Okay, first of all, before we begin, let's actually try to get the actual formula using some tricks or ideas called the Pappus theorem. Now, what Pappus theorem says is, let's say if surface or a volume is generated by a generating surface which is basically moving or rotating. In that case, we can use Pappus theorem to get the volume covered or surface area covered, right? So in this case, and what Pappus theorem says is the volume covered will just be area of the generating surface, right? So in this case, this circle, which is basically a revolving round a center to generate this torus, right? So area of generating surface times distance traveled by center. So distance traveled by its centroid. Distance traveled by its centroid. It's here it refers to this generating surface. Now in this case, center of circle is of course the usual center. Yeah, for triangle it's the centroid. Yeah, and yeah, there are for not random surfaces like this, we need to use integrals to find the centroid of such shape, and that is basically just center of mass if the body has uniform mass distribution, right? And you can also, there are formulas to find the center of mass using integrals, right? You can google them, just over the domain integrating yx, but that's beyond the video, beyond the scope of this video, so we will not go into that. Okay, so yeah, there's something like this. Okay, so anyways, you can google that if you want to find how to find center of mass of irregular bodies using integrals, but for now it's easy because our generating surface is circle, the center will just be the usual center. Now the area of our generating surface, let's say if this length is b, and if this length, the distance of the to find the distance traveled by centroid in this case, we'll of course need this radius, right? The distance from center of torus to the center of this generating circle, let this be a, so that this travel distance will be 2 pi a and its area will just be pi b square, right? So the volume will just be basically pi b square times 2 pi a. So yeah, it's 2 pi square ab square. So that's the volume. We will try to put this using calculus as well, right? And the surface area, is also somewhat similar. Just the circumference, or let's say the arc length of generating figure or whatever, generating figure times the distance traveled by its center, again distance traveled by the center, distance traveled by center of generating arc length, yeah. Now in this case, the arc length is basically the circumference of circle, right? Its circumference. Since we want to find surface area, this curved surface area of torus, so yeah, the distance traveled by circumference, right? The length of circumference times distance traveled by the center of this circle. So again, that will just be 2 pi b times 2 pi a. So surface area is 4 pi square ab. So these are the formulas for surface area and volume of the torus. But now we want to use calculus to find to prove these things, right? Now to use calculus, of course, we need to know the equations that give this torus, right? The equations that will generate the torus, and if we have equations, then only we can do the calculus, right? And the general idea is, if you have, let's say, equations that give this torus, then we can just integrate to find the surface area. We can just integrate over the domain of surface area element, right? I'll go over it in some moment. Similarly, to find volume, we can just integrate over the domain, which we write E in 3D, right? We can just integrate over that domain of volume element, right? So yeah, so we will be doing these things. Yeah, but first of all, we need to be able to get some equations that generate torus, right? And notice that, first of all, let's set up the coordinate axis and let us talk about like what kind of equations would be possible. Let's say this. Let us say that this torus stands in the standard position. Guys, don't get like afraid of these things. Okay, like I mean, it will not be too complex actually, if you are thinking so. Okay, let's place this torus in standard position. That means basically the half of torus is above the sorry. Basically, the half of torus is above the xy axis. I mean, above the xy plane, and half of torus is below the xy plane, so that the xy axis is basically exactly going through the like middle of this circle, right? And yeah. So now, if you just try to like find equations like in the form z is equals to f of xy, that can be really hard. The first thing is the g x and y are restricted because like there are no points in this domain or outside this domain, right? There are no z x y z values. X and y are restricted, and that restriction might be really hard to write because it's a curved surface, right? So yeah, that can get a little harder. So what we'll instead do is we'll try to write we'll try to like equationize or something like that. We'll try to find these equations in terms of vectors, in terms of parameters. Okay, so what we'll try to do is we'll try to write a parametric equation that gives the position vector for all these points on surface of torus. Yeah, we'll try to do that. So for that, what we can do is let's try to take a general point on the torus and then try to find the using different parameters. Let us try to find how we can get that general point in torus. So let's say there's a circle. So also notice that we only want to parameterize the surface of torus, right? So we will be taking a point on the surface of torus. So let's say this is the center of this circle over here, and yeah, so we want to find this is our like required point. Okay, so let's say this has coordinates y, x, y, and z. X, y, and z. Okay, now it's really easy to find. It's basically this x, y, z are three different coordinates that make this vector. Okay, so that makes this vector, position vector, that's giving this point. You can see it as both as vector or point, but yeah, you need to know that basically we will write a vector in terms of few parameters that will give all 3 points. And yeah, these 3 points, when we plot all these points, we will get this surface. So that's the idea. Now, okay, for this point, if you want to get a z coordinate, that's really easy because we know that this point, this center of this circle is basically in xy plane, right? So we just need to find this height, right? Now, if we just let this angle as let's say this radius of this inner circle is b and this angle as beta, this height from the xy plane will just be b cos beta, right? So our z coordinate will always just be b cos beta, where beta is that angle with the xy plane that the point makes. So b cos beta, and we know that if we vary this beta from 0 to 2 pi, we will basically just get the z coordinates of all these points on this circle, right? So for a given x and y, like varying beta, per given b, if we vary the beta, we will get the coordinates of all these points on this circle, right? Now for other points, now notice that b sine beta will be this length over right there. This length over here will be b sine beta, right? And now if we say that the distance from center to center of circle to center of torus is a, if this length is a, right? Then this entire length is just a plus this entire, let's say if we call it r, this entire length r is just a plus b. Oh wait, this height is actually b sine beta, I'm sorry. This height is actually b sine beta. Now this length will just be a plus b cos beta, right? A plus b cos beta. Okay, now since this r is a plus b cos theta, because beta, and we know that it's in xy plane, for now it's easy to get the x and y coordinate, right? They are just these components. Yeah, they are just these components. I guess you can easily see that. Now if I just name this angle over here as alpha, which will also be derived from 0 to 2 pi to give the entire torus, right? Our x coordinate of this one will just be the x component of this r, right? And which is basically just the a plus b cos beta times cos alpha, and its y coordinate will just be again this r times sine alpha. So you see that this x, y, and z, let's say there's a vector u and v which takes 2 inputs and gives 3 output, right? So in a new coordinates, okay, so basically if it takes u and b, where u and b are between 0 to 2 pi, right? So for these points, if it takes these 2 points and plots this a plus b cos beta times cos alpha, a plus b cos beta times sine alpha, b times sine beta. These will basically gives the vectors that will just point on the every point in surface of like the torus, right? So these will basically gives the position vectors of all the points on the torus. If u and b are, no, not u and b, alpha and beta, I'm sorry, if alpha and beta are allowed to vary in this domain, this will basically give the position vectors for all the points on the torus. So that's how the parametrization can be helpful. This parametrization will help us to get all the position vectors for all the points on the torus, right? So now we know that. Now we want to know how to find the small surface area element, right? Now, okay. Now we know that this r vector of u and b gives the points on torus, right? Now let's make one more copy of this. Now we have that, guys. This parameterization on all these things, we don't need to do it again for volume. This is the first time, so yeah, it can get a bit long, but don't worry about that. So right now we have known that this r vector of alpha and beta, and only alpha and beta will vary, a and b will not vary, right? We know that a and b are just fixed numbers. A is basically this length from center of torus to center of circle, and b is basically this length, the center of this circle, right? Yeah, this is not beta. Okay, I'm sorry again, this is not beta, this is just b. It looks like beta, no, this is just b. Okay, also this is just b and this is not beta. Okay, now we know that for alpha and beta, while if they go from 0 to 2 pi, and I guess you know why 0 to 2 pi, right? For this entire points on the circle, beta needs to go from 0 to 2 pi, right? Again, this alpha need to go from 0 to 2 pi for all the circles. So yeah, and if we plot a plus it was b cos beta, and then cos alpha for x coordinate, and a plus b cos beta and sine alpha, and then b sine beta. If we plot, and notice that this parameterization could change. Like let's say if I have taken, like instead of beta, if I had taken, let's say this angle as gamma, in that case our x coordinate will be b uh, cos gamma, right? In all other these things would be sine gamma, right? Even in that case, if you vary gamma from 0 to pi, we will still get the torus, right? But this is just the standard parameterization. It's not necessary that there's only one parameterization. There are a lot of them. This one is just how what we use often, so I'm doing that. Okay, now we have got this one. Now we want to find a small surface area element. So for that, I want you to observe a few things. So let's say if I input alpha naught and beta naught some values, let's say I get a position vector which points on certain point of in the torus over here, right? Now if I increase alpha by certain amount, let's say some alpha del alpha, keeping b constant, this r vector will point in some forward direction over here, right? So now this is basically the change caused in the r vector due to the change in alpha, keeping b constant, right? Now we have some things these things called partial change in r due to partial change in a. So what this means is the rate at which the r vector, the value of the r vector, which is basically the change we can see over here, right? The vector went from this one to other one. So this change, so yeah, the change in the r vector by change in a vector, the rate at which that changes if the b is constant. So that's what this means. And yeah, so we are dealing with the same scenario. And if I multiply this with the change in a, this will basically give us how much the r vector will change with a small change in a. The amount, this is the rate of change, and if I multiply by a small amount, this gives us the small change in the r vector due to change in a, right? So this one over here, this vector will basically be change in the r vector due to change in a, keeping b constant, times the amount of change in a. So this will basically give the change in r vector due to change in a. And similarly, let's say if I keep alpha constant and if I change beta, let's say it changes like this. Let's say this is the change, and this change is basically due to change in beta, keeping a constant. So yeah, and if the amount of change in beta is very small, let's say yeah, this is the rate of change of b r with respect to beta. Guys, this should be alpha, because why I'm saying a, this should be alpha, guys. Okay, now the rate of change in r vector due to small change in beta times the amount of change in beta, that will give how much amount the r vector changes due to change in beta, right? So this is yeah, r vector by change in beta times d beta. Now over here, now why we're just dealing with like keeping one constant, keeping other constant, the reason is while integrating also in this case, while let's say alpha is going from some values to other values, even in this case, while alpha is a fixed value, b will be changing, right? And there will be like the differential elements, basically d beta, d alpha. While alpha is constant, in this case beta will be changing and we will capture in the volume, right? So yeah, with the basically, because the scenario is same over here, we have just found out how much does the r change with small change in beta, and how much does the r change with small change in alpha. So now we want to find out this small change in the area, in the surface due to small change in alpha and beta, right? Now how we can find this area? So basically, to find the area given like with two vectors forming a parallelogram, right? Note that these two vectors will make a tiny parallelogram, and all such changes due to the alpha and beta in the r vector, if we just add all the small parallelograms, we will get the entire surface area, right? So yeah, now to find that area, we can just take the cross product, right? We can just take the cross product of these two vectors. and find its magnitude. Note that we cannot just multiply d alpha and d beta, because this is not a like a rectangle where like those vectors are perpendicular to each other. Since it's not like a rectangle, so we cannot do that, because it's not necessary that d alpha and d beta be perpendicular to each other, right? Yeah, so find the cross product and then take the magnitude to get that small surface area element. So we know that these two are constant, so they can just go out. So we get small change in r due to alpha cross small change in r due to beta times d alpha d beta. This is the small change in surface area, right? Now what we will do is, so while alpha goes from 0 to 2 pi and beta goes from 0 to 2 pi, we will just try to integrate all the surface areas, right? So that we will get all the surface area in the torus. And we know that now in this domain, the surface area is just partial r by partial alpha cross partial r by partial beta times d alpha d beta, right? And basically this is the limits of alpha, this is the limits of beta, and since they are same, it won't really matter like the order, right? And yeah, now we need to just calculate this integral and we'll get the answer. Now let's try to calculate the partial derivative of r with respect to alpha. Partial r by partial alpha, and this will be minus of a plus b cos beta times sine alpha, a plus b cos beta times cos alpha, and then there's no alpha, so that's just 0, right? Okay, and partial change in r due to beta, that will just be now this is due to beta, right? So minus b cos b, sorry, minus b sine beta, minus b sine beta cos alpha, right? So basically, I think you know how to calculate partial derivatives, right? We will just assume other thing as constant and just take the derivative with respect to this variable that's over there. So that's I'm going to do, that's what I'm doing, and I just hope that you understand it. Yeah, this should be like prerequisite. So for here, since a sine, if we find the product, a sine alpha will just be constant with respect to beta, so that will be 0. And then b, for b cos beta sine alpha and b are constant, and cos beta is minus sine beta. So minus b, that's how it's working, minus sine beta sine alpha, and then that will be just b cos beta. Now let's try to find the cross product. It can get a bit messy, but yeah, we'll just do it. This will simplify it last though. So dr vector d alpha cross dr vector d beta, that will just be I j k. I need to make some space over here because these expressions are long. I j k. Okay, minus a plus b cos beta sine alpha, a plus b cos beta cos alpha 0, minus b sine beta cos alpha minus b sine beta sine alpha b cos beta. Let's see value determinant. This idea of a cross product is also prerequisite. I guess you all should know this, right? Now this is just b times a plus b cos beta times cos alpha cos beta, right? Now there will be negative j, and the product will again be minus b a plus b cos beta times sine alpha cos beta. Is this it? Yeah. And then k times, it will just be b times a plus b cos beta sine square alpha, and then plus b times a plus b cos beta sine beta cos square alpha. Notice that over here, if we take if we just take b times a plus b cos beta common, and then sine beta also common, we'll just have sine square alpha plus cos square alpha, which evaluates to 1, right? So I can actually write this as, b times a plus b cos beta times sine beta, right? Okay. This will further simplify when I take the magnitude, so don't worry guys, it will not be that hard. Now if I want to find the magnitude of this picture, also notice that this will be plus plus, right? Okay, due to multiplication. Now if I take the cross product, magnitude of this cross product, it will just be square root of, and notice that this b times a plus b cos beta is same everywhere, and yeah, so everywhere there will be square of this thing, so we will just take common that in the beginning itself, because its square will be in every component, right? Now over here there is cos square alpha cos square beta plus sine square alpha cos square beta plus sine square beta, right? Now this is b times a plus b cos beta. Now this is, if I take cos square beta common over here, I will just have cos square alpha plus sine square alpha times sine square beta, right? And now this is b times a plus b cos beta. It's just square root of cos square beta times 1 plus sine square beta. So this is b times a plus b cos beta. This is just 1, so that is b times a plus b cos beta. So we see that this cross product is just b times a plus b cos beta, right? So let's substitute that over here. 0 to 2 pi, 0 to 2 pi, b times a plus b cos beta, b times a plus b cos beta times d alpha d beta. Now this is 0 to 2 pi, 0 to 2 pi. Let's write it as ab times b square cos beta d alpha d beta. Now since these are just constants, and now I can just write it as 0 to 2 pi d beta, 0 to 2 pi d alpha. We can just separate the integrals, right? If the numbers are just constant and the functions aren't mixed. Again, b square 0 to 2 pi cos beta d beta times 0 to 2 pi just d alpha. And this is ab, this is 2 pi, this is 2 pi plus b square. This one will be 0, that will just be 2 pi. Now it will just be 4 pi square a square ab cube, 4 pi square ab plus b square times 0. I mean that's just 0, right? So yeah, 4 pi square plus 0, which is just 4 pi square ab, and that is the answer, right? So we got, using calculus, that surface area of torus is just 4 pi square ab, which is exactly what we have got over here, right? So now let's go with the volume of torus. Again, let's make copy of this one. Again, for this one, again, we'll just slightly change the parameterization. There will not be a lot of change, right? Now let's duplicate it. Let's make a duplicate. And now this time we need to get, okay, first of all, let me make a duplicate. Duplicate. Okay. Now this time we need to make a parameterization such that we get all the vectors, even those, center. We need to get all the vectors and even those which are inside the torus, those in the surface as well as those inside, right? And it's not that hard. Like previously we just assumed this radius as b, right, which just gives us points on this surface. But if this radius is smaller, that would give points on this surface, right? So this time we will not keep b as constant, we will just let it be r, and r varies from 0 to let's say b, right? 0 to b, yeah. This time we will also make that consideration. And if we make that, now we will have um, a vector which takes alpha, beta as well as radius, right? Now it seems like there are two r's and that can be confusing. So I will just make this. Now how do I deal with this? Let me just say this as vector only. Though it's like notion, it's a position vector. Let me just say position vector for with alpha, beta and r. So that will just be, now this time that will just be a plus r cos beta times cos alpha. This is the same, just the b change. Now a plus r cos beta times sine alpha, and this is r sine beta. So this vector will basically give all the vectors inside the torus, in the surface of torus, and all of these, right? And we just want to integrate over this entire domain where basically r is going from 0 to b, alpha is going from 0 to 2 pi, beta is going from 0 to 2 pi. Over this domain we just want to integrate the volume element. Now how to find the volume element? Now again we will use the same technique, right? Now like maybe just as previously, it alpha naught, beta naught, r naught, let's say they give a position in Torus. I'll just point over here. Let's say they give this point, right? Now this function, it's difficult to write it as pb every time. I will write it as, let's say, f. Now this function, but there is no, but people don't use f, right? Capital R, will you find? Okay. Now this is called radius because this is like position vector and that's length from center, right? So yeah, that's fine. Now let's say with respect to alpha, it changes in this manner. Let me say it may not go straight. So okay, so yeah, this is the change in the r with a small change in alpha. So yeah, the rate of change with respect to alpha times the change in alpha, that gives a change in r due to alpha. Now let's say this is change in the r due to beta, and with respect to r, let's say it changes like this, right? And yeah, oh okay, so let's say this is change in r due to r, the small r. Yeah. Now basically like normally if this thing adds some volume, these three things will not be in the like same plane or same span, right? They will have different spans. Now how to find the volume? Now notice that again in vectors we should have read that if these two vectors, if you want to find the volume that's encompassed by these three vectors, right? With these small three changes, there are changes in alpha, beta and r, right? And those three changes will make a small change in volume, right? And that thing, this 3D surface is just a parallelepiped, right? This is just a parallelepiped. Yeah. Now to find its volume, what we can do is we can first find, let me, if I name this as x vector, y vector, z vector, we know that x vector cross y vector will just give the area of this parallelogram, right? And if I dot this with z vector, what this will, though it will not exactly be x or in x and y direction, it's not necessary, right? Just I'm just naming this. And if I dot this with z, basically what happens is this will give the area, and then dotting with z, that means x, y, if this angle is alpha, and z will, basically this vector will be in perpendicular direction. And now this angle, if it's alpha and if this is beta, I'm just making it a lot complicated. This will be x, y, sine alpha, and then again this will just be, again this will be modulus, right? Modulus of z times that will be cos beta, right? So I will just get the height of the area times just the height. I will not get the entire length of G vector, but just the height that this parallelepiped has, due to which this will just be the volume of parallelepiped. I wanted to explain that, but it went a lot miss, But yeah, I think you have read that this will just give the volume of parallelepiped, right? Volume of parallelepiped, and this is also called the scalar triple product, and it's written as just x y z, just like this. And yeah, this basically means the like this x cross y dot z will give us the volume of parallelepiped. And since we know that, and to evaluate this is a scalar thing, how you do is, first of all, you take their cross products and dot with it, right? So if let's say, if I have if you the cross product of these two things will just be I j k times x1 x2 x3 y1 y2 y3, right? Now if we dot this with this z1 z2 z3 vector, basically it will just come in this first one, right? When it's dotted, like one, there will be one to one multiplication, so we will just get this determinant, right? Z1 z2 z3 x1 x2 x3 y1 y2 y3, right? And this is how we find the scalar triple product. I guess you guys know that. Just in case if you don't, I'm just saying this dotted. Okay, so this is how we find scalar triple product, and we also want the scalar triple product in this, right? Because we want the volume. So in this case also, our dv will just be the scalar triple product of these vectors. So first of all, we want the scalar triple product of this vector, partial the change in r due to alpha, this vector, cross let's say another, we take it this change in r due to beta, this vector, and then dotted with the last one. We can take any of them, right? The order won't matter, I guess so. I don't know, but yeah, we are just taking the base and then the height. This thing makes sense, so it should work, right? Now dr by partial r times dr. Okay, now this is our dv, right? And now these are just constants, so you can take it out. You can just take it out, and we can write it as partial r by partial alpha cross partial r by partial beta dotted with partial r by partial r times d alpha d beta dr. Okay, this is our dv, and now we can find this by using determinant, right? Just as I have said over here. And now, so this will just be equals to, this will just be, okay, right over here, this will just be equals to, this vector will be it's in second row and third row, but that won't matter anyway. Okay, let me write it. So let's say this vector will have the components, the change in r due to change in alpha, right? So since r also consists of, okay, now we know this thing, we'll do it later on. We will not derive formula right now, we'll do it later on. Okay guys, we'll just do it later on. Okay, now over here we know that this will just be from 0 to b. Wait, I'm sorry, how do I delete this? Oh, it's not being deleted. Nice. Okay, now, so while r go, we now know the dv element, right? So yeah, we'll just do it now. So while r goes from 0 to b, alpha goes from 0 to 2 pi, beta goes from 0 to 2 pi, dv is just partial change in r due to alpha cross r due to beta dotted with r due to small r, right, times dr d. Okay, again, this order need to match with the order of limits, so this should be d alpha d beta dr. Okay, just to match the limits. But I think usually normally people don't write it this way, so let me go with the normal convention. People write it in different way. Let me just go with that. First of all, let me give it for alpha 0 to 2 pi beta 0 to pi, and then r 0 to b, right? This is dr d alpha d beta. Okay, now that works. Now let's try to find this cross product. Okay, so in the cross product we have okay, now dr divided by d alpha. This is just a plus r cos beta minus sine alpha times a plus r cos beta cos alpha times 0, right? This with respect to beta, actually we have already found this in previous section as well. So yeah, so I guess you have the idea now. So minus r sine beta cos alpha, comma, minus r sine beta sine alpha, comma, r cos beta. And dr with respect to r is just cos beta cos alpha times cos beta sine alpha times, okay, now this is just sine beta, right? Now we need to first take the cross product and determinant, and which we just know that this scalar triple product will just be the determinant of entire thing. That, right? I already told you that that thing of how to take this scalar product. So this will just be determinant of entire thing. So alpha, for the sake of understanding, I'm just writing it in the same position that you guys would think it would be, right? The alpha in the second, beta in third, in the r will come over here as dot product, right? So that's just for the sake of understanding. But I don't know, like maybe the sign changes with changes in row. I'm not sure about that. So let's just write how the things are making sense, right? Let's not be over, let's not go in a different way. Things are making sense, so this should work. This should work, and that's how we do it. R cos beta. Oh wait, this should be. I'm writing it wrong. This is a plus r cos beta cos alpha times 0 r cos beta, and this is cos beta cos alpha cos beta sine alpha sine beta, right? Note that I could have just dotted it with the things that we have already got over here, because we had already got this vector, right? That cross product over here as well. I could have just easily dotted with that, and that would have easily worked. Fine, I can just go over here as well. Now this is just cos beta cos alpha times, this is a plus r cos beta times r cos alpha cos beta, right? Now minus cos beta sine alpha, that will be multiplied with a plus r cos beta times r, that minus alpha sine alpha will make it plus, and then sine alpha cos beta, again minus sine beta times, that will just be a plus r cos beta r sine square alpha sine beta plus is this really minus sign? Should that minus sign be there? Am I doing it right? A plus, wait, let me check, because I think there is some mistake. A plus beta minus sin alpha, a plus beta times. Wait. What's our original function? So a plus r minus sin plus beta times cos alpha 0, right? Beta minus sin beta cos alpha minus cos beta, right? And then cos beta cos alpha cos beta sin alpha sin beta. Okay. So cos beta minus cos beta minus sin alpha. That seems to be true. Is this same as the previous one? Do you get the same thing? Are you getting the same thing? Beta b plus a plus or equals b a plus b equals beta sin cos beta, and then beta times. I think that's same, right? But how come there's no minus sign over there? Oh yeah, this should be plus. Why I'm writing it minus actually? This should be plus, right? Again, there's a plus. Okay, now it's working. So we have cos alpha a plus r cos beta, and then r sine beta cos alpha. Now if we add this, you can notice that there's this cos square beta cos square alpha times r a plus r cos beta plus cos square beta sine square alpha times a plus r cos beta times r plus there's again, if over here if you just see, this is sine square alpha sine square beta times a plus r cos beta times r plus, now over here it's cos square alpha. It doesn't appear, that cannot happen. Cos alpha sine beta. Oh, is that the case? But how did this appear then? Sine. Okay, this should also be sine beta. There should be also a pair, right? Because the sine beta will multiply both. Damn, I just forgot the things. Okay, now there's a pair. Sine cos square alpha sine square beta times a plus r cos beta times r. If we evaluate this, if we take this cos square beta r, all these things common, there will be cos square alpha sine square alpha, which will add up to 1, right? So this will be cos square beta r times a plus r cos beta plus, now if we take sine square beta common, there will be sine square beta common, there will be sine square alpha plus cos square alpha, which will add up to 1. So sine square beta times r times a plus r cos beta. Now if we take r times a plus r cos beta common, there will be cos square beta plus sine square beta, which will again add up to 1. So r times a plus r cos beta. So this is our dv element, right? And I want to tell you something else as well. Now basically, you must have noticed that this determinant is also called Jacobian determinant. And yeah, people usually just start with that, and that's not really necessary. So yeah, I didn't do that, but yeah, if you want to formalize this thing, this argument, like just you can just search about Jacobian, and that will give me like formal argument. I mean the formal way of doing these things, but that isn't really necessary. Now let's do this. This is from 0 to 2 pi, from 0 to 2 pi, from 0 to b. And now this thing, we have just evaluated that it's actually equals to r times a plus r cos b, right? R times a plus r cos b. No, I don't think it's b, it's beta. Oh yeah, it's beta. B shouldn't be there, right? B beta. Okay. Again, to evaluate this now, we know that this will now just be AR plus AR cos beta, right? And DR D alpha D beta. So now again this will be 0 to 2 pi. Now okay, over here this A is just a constant, and there's nothing for this one. Alpha 0 to, we're just trying to break the integrals d beta and 0 to b r dr plus, now for this again A is a constant, for this would actually have been beta and then alpha, I'm sorry, beta and alpha. Now with this one, this should just be cos beta d beta, 0 to 2 pi just d alpha, and 0 to b r dr. Now this will be a times 2 pi times 2 pi times r square by 2, which is b square by 2 minus 0 0. A times this is just 0. It doesn't matter what the rest of the thing is. This is just b square by 2 anyway. Okay, now this is 2 to cancels out, so this is 2 pi square ab square plus 0. So the volume of torus is 2 pi square a square ab square, which is what we have here as the original prediction, right? Yeah, 2 pi square ab square, it's over here. So yeah, we have finally used calculus to derive all this, and that was a lot of work actually to parameterize this and to derive the surface area element, volume element, and all those things. And yeah, if you had completely watched this video, if you paused it at some point and tried to understand it on your own, if I did not make sense, if you had just done a little bit of work on your own, I think that this will give you a lot of intuitions, because yeah, sometimes it might not even be given in the class, right? Like how that dB element is derived or anything like that. So yeah, this can definitely help me a lot if you were serious in doing this, right? And yeah, I just hope it was helpful. And if it was helpful, do share with your friends. Thanks for watching. This is my third attempt in making this video, and yeah, I think it has gone okay. And yeah, look forward to seeing you in the upcoming videos too.